to unfamiliarity and the scalability of recognition. Perhaps most relevant to this workshop is his work on learning aligned image-word representations for vision language tasks and finding focus regions in images for VQA. Today, Derek is going to talk to us about dangers and opportunities for research with VQA. We look forward to hearing from you.
Thanks. So I've always been really excited about VQA. It's, as people often say, a visual Turing test. But on the other hand, you usually don't directly prepare for an IQ test. And so there's kind of a question of how is this something that can drive research and something that we can use to help our vision systems learn and develop new capabilities. So rather than talking about my work, I wanted to kind of look at VQA as a research problem. And so I surveyed the papers that I could find that had at least 10 citations, including survey and analysis papers. And I wanted to understand and talk about how is VQA used for research. And I was particularly interested in what are ways that we can better evaluate to help facilitate the most interesting research problems in VQA. And I just want to mention there's a nice survey if you're ever interested in just kind of getting a quick glance at the problems that people have worked on. There's a survey by Wu et al. So first, it's clear that VQA offers the opportunity of a lot of unique challenges. So there are several problems that you can study on VQA that I think it's a better data set to study than any other data set out there. So some of those are that you've got disparate vision tests that are specified by natural language. And so you can study problems like embedding and grounding or inductive transfer from other data sets. It also requires a wide range of specialized skills, as Lana was focusing on. And so compositional models are a really interesting way to try to address that problem. It requires new forms of task generalization. You can think of every new question as a new kind of task. And often that requires information that's not present within the training set. And so that requires external knowledge and, again, inductive transfer from other data sets. And then there's also a variety of problems like that. Some questions are really hard to answer. And so maybe instead of trying to answer it and knowing that you're probably going to get it wrong, the system could say, I don't know, not only because it's unconfident, but because it might not have, it knows that it's in an unfamiliar territory. And so actually there's people working on all these problems, and I was really encouraged to see the diversity of ideas that people have been proposing that are inspired by the VQA data set. One thing that's kind of clouds on the horizon, I guess, is that there's every now and then, I mean, it's only been 2 years, but there's a baseline paper every year that comes out and says all these interesting things that you've been doing are trumped by my really simple system. So there's this paper by Jabri et al. Basically concatenate bag of words model for questions and answer, and then the visual features, train a multi-layer perceptron, and it does better than a lot of more complicated systems. So evaluating on like overall accuracy, yes, no, number, other, et cetera. One thing though, and I guess what this shows to me, or to date, I would say, according to these evaluations, all the interesting ideas about attention and using external knowledge and compositional models tend to be, their effects are small on the entire VQA problem compared to the effect of getting a better feature or some of the details of your training. Are you using a TAN-H or some other activation function? And so Jabri et al. Conclude that the best performing methods are those that are best at cheating, that they can fit the data set biases, or maybe that current models are not ready for VQA and they hit the same ceiling. And they conclude that it might be necessary to consider alternative evaluations. What I think is those are reasonable assessments, I suppose. I think what's really happening, though, is that there's so many different details in these systems. They're often comparing one system trained on ResNet that's pre-trained on several different data sets with another one that was using AlexNet and they didn't pre-train at all. And so it's often an apples and oranges comparison, and then you're looking at the overall accuracy, which is trying to combine, the best common denominator is really going to be the system that performs the best. So I think that the danger of VQA as a research problem is partly due to the current standard evaluation. So in the current setup, I think that VQA really encourages pattern matching approaches because you've got an enormous training set, 200,000 examples. And so what you can learn to do, and some of the analysis papers show what the systems do actually do, is you take your new question and image, you match it to the most similar one that you see in the training set, and produce a similar answer. And if that kind of strategy fails, then most systems will do a bad job at providing a correct answer. It also, because most papers are evaluating only on overall accuracy or on that very coarse division, it really encourages doing well on the most common questions, which means that you don't really need to generalize that well or do well on novel words or the heavy tail or more rare types of questions. You just do well on the common ones, and that will boost your overall accuracy. So as a result of that, differences in features account for a lot of the variation in accuracy. And research contributions that impact a subset of skills or try to deal with the heavy tail have little measurable impact. And I think that I think as the danger is basically that some of the most interesting directions are in danger of being undervalued, especially if what people really want to see is driving up the numbers in the evaluation. So the question is, how can we maximize the opportunity and minimize the danger? So I wanted to see how do people currently, so I guess as I said in the danger, I think the danger is coming from the way that most people are evaluating. And so I wanted to see how do people evaluate? What are all the different ways that they quantify their performance? And I want to say that sometimes I'm only looking at how they evaluate quantitatively using VQA. Sometimes people create toy data sets and they have really nice evaluations for their systems. But this is just focusing on how they use VQA to quantitatively evaluate. So everybody does the standard breakdown, which is that you look at overall performance for yes, no questions, number, and other. There's a few papers that do a customized question breakdown. So this is mainly my group and Anton's group. So this can be useful because then if you're, for example, doing attention, we know that for what color questions you really need to have a good attention model or be able to focus on the right thing. And if you don't have a good attention model, then it will do bad on what color. And if you do, then it will do well. So by looking at the types of questions in more detail, you can often predict which questions you should improve on and then measure larger improvements in those areas. The thing is, though, that it's a customized question breakdown. So every paper has a different breakdown. You can't compare across papers. There's also, for attention, a couple of papers analyze attention over a small subset of the data, often with some kind of manual annotation. The most comprehensive evaluation is Dataset et al., where it's a rank correlation. I'll talk more about that later. And then for generalization, there's the paper Agrawal et al. Analyzing the behavior of VQA systems, where they correlate the accuracy and distance to the accuracy of a system on questions and the distance of those question images to question images in the training set to evaluate the generalization behavior. But basically, this is looking at maybe 25, 30 papers. So most of them are just relying on the main breakdown, the main overall accuracy for the quantitative evaluation. And so I'll often see papers where they say, we've got a great new attention model, and look, we do 1% better than these other papers. And by the way, we also have updated to the newest architecture and changed these details and these details. And so it's kind of hard to see if they really have made the contribution that they've claimed. So I want this to be not as much of a criticism or I guess I don't want to just talk. I want to actually have action items. So I want to make some proposals for ways that we could, yeah, I can send the slides. I want to make some proposals for how we could extend the evaluation and hopefully do it in a standardized way so that we can compare across papers. So one idea is a skill type attribute. So this is kind of similar to question types or answer types, but really you can't always tell what skills are required just based on the question or based on the answer. So there's, as Lana said, there's a lot of different skills that are required for solving these VQA questions. A single question will typically only require one or a few different skills. And so one idea is to tag each of the question answers with these skill attributes. So for example, is the light on the train lit? Yes. This requires being able to identify an attribute, lit, an object, doing spatial reasoning, the light is on the train, and grounding, you need to focus on that area. Another example, is this a polar bear? If you just have an ImageNet object classifier, it could answer this question, so it's really an object skill. What sport is the man participating in? Surfing, it's an activity. And then, does this bag belong to a male or female? So this requires recognizing the bag, the attributes, grounding, possibly external knowledge in order to recognize that the things outside of the bag are more likely to be owned by women. And so likewise, for each of these questions, there's different kinds of skills. And so what you could potentially do is if we've tagged the question answer or the question image answer triplets with the skills, then you can predict which of the skills will your system improve, and you can look at your improvement in particular subsets of skills. So if your paper is like, how do we count objects in natural scenes, it doesn't really matter what your performance is on overall VQA. You want to see how your performance is on counting, or if you're trying to look at the effect of external knowledge, then that's really only applies, or it's really only useful for a subset of questions. Another common problem that people look at is attention. And so, as I said, I think that this data set created by Dataset is a really useful way to get some insight into whether your attention model at least is really an attention model in the way that people think of attention. So in this work, they asked people to expose parts of the image that would be helpful for answering the question, and then analyze the similarity of human maps and computer maps using Spearman's rank correlation. And one of the findings is that a lot of the existing methods actually underperform a center bias or a salience map. So if you just assume that the center of the image is the most important, and then there's a fall off from there, you actually do pretty well in predicting human attention maps. And salience maps also have a center bias in them, and so they do about as well as a center bias. So one thing that you can do to maybe break that down a little bit is plot the performance of attention maps as a function of the degree of center bias of the question answers. So here, I also propose like a slightly different metric than Spearman's correlation that takes into account the strength of the attention and the strength of the difference in the human attention maps. But here I'm plotting as a degree of the center bias for the images, how well different systems do in predicting human responses. And so at the top line is the interhuman agreement, which of course is the best. That black line that's kind of going up diagonally is the center bias. And then there's a bunch of these attention systems, and then the SAN2 system, the spatial attention networks, and then a new thing that we have is the circles on the top. Another thing, though, is that you can also, it always kind of bothers me, the idea that you can have a fixed attention map that's outperforming all the other systems if you look at all the whole data set. And so another thing you can do is, instead of looking at the correlation of the position across, instead of looking at at the pattern of predictions within each image, you can look at the pattern at a single position across the images. And so then any fixed map will get chance performance. So in this metric I'm using, chance performance is 0.5. Salience does barely better than that. And then you have a way of controlling for center bias, basically. So I think these are good ways of evaluating whether your attention model conforms to that of what people think is important. And it would be nice if kind of there were a standardized way, just picking some kind of metric so that people can compare, does my attention map conform to human maps? Another major problem is generalization. So VQA offers really interesting and unique generalization problems. You have to extend to new types of questions, to novel objects, and so on. And there's been a few different metrics proposed for evaluating generalization. So you could, for example, look at what's the probability of the question-answer pair according to some kind of generative model, like a trigram. You could look at what's the probability of the least common word, or as the Agrawal et al. Did, the distance in some learned metric space between the question-answer and the question answers that we're seeing in the training set. I think it's not really that important exactly how it's measured, but it would be really helpful if you could also tag all the question answers with a kind of rareness score. And then when you're evaluating, you could do a breakdown of how well do I do on the really common questions, and then how well do I do on the questions that are more rare. And so people that are really trying to focus on the heavy tail could then demonstrate or fail to demonstrate that improvement. Another thing that I think would be really interesting is to have a really tiny training set. So obviously, if you only have 1,000 training images, you're not going to learn everything that you need to know from the VQA data set itself in order to do well on the test set. But for these, there's a lot of, I think it's a big problem in computer vision of how do we build vision systems that have acquired some kind of core representation and then can generalize that to new tasks. And so a small number of images may be enough to just help it adapt or define what this new task is. Like, what does it mean to answer questions? And so this would be another way to evaluate generalization. If your system can really adapt to a new task well, then it should be able to learn from a small number of examples, even when there's insufficient information in those examples itself to solve the larger task. This is slightly different. So another thing that I find that's kind of creates some confusion or makes it hard to compare papers is that since there's both an open-ended and a multiple choice way of answering the questions, sometimes people do one or the other, or they do both. In my view, the way that people usually do open-ended is by turning it into a large multiple choice. And what it really tests is how good is your system at winnowing down the set of possible answers into those that are likely based on a prior. So for what color question, your system's not going to answer yes or no. It's going to boil it down to a few colors based on the questions and answers that it's seen before, not based on image content. So because multiple choice is a cleaner evaluation, and because I think that open-ended tends to further emphasize the importance of learning what's often called like the language bias, I would advocate for people using multiple choice more, but obviously that's an opinion. So in conclusion, VQA creates a lot of opportunities for studying task generalization and for learning to perform tasks specified with natural language. I think there's really interesting problems that many researchers are studying that is made possible by the VQA data set. The concern is that current evaluation standards might inhibit the research by encouraging treating VQA as multimodal pattern recognition. There's nothing wrong with studying multimodal pattern recognition, but there's lots of other ways to study it that are more direct, or especially studying pattern recognition in general. So my proposal is that we should create a standardized extended evaluation. I think it's important that there's a standard and that it's associated with the VQA data set so that it provides some legitimacy to those who use it and that it facilitates comparison across papers. And so some ideas I have, although everything has to be specified more precisely, is the use of skill type attributes, having some kind of metric for how good your attention maps are, some metric for how well your system generalizes, and then possibly having like a mini train set challenge. So thank you very much.
Thanks, Derek, for such an interesting talk. We can take questions now.
Hi, thank you. I agree to most of the points. I'm not so sure about the open-ended versus multiple choice. For the reason is that you can suddenly build different models if you have the answers and can embed them. And with such a model, while it will solve this task, you can not really go out in the open and really answer a question because you always need those multiple choices. So it might be good to author evaluate it, but I think modules should also be able to just answer all questions. I sort of have this more like open-ended setting.
Yeah, I think that's a reasonable point. It also goes the other way. Sometimes a system that can easily generate an open-ended answer needs to be adapted in order to do, maybe need to be adapted to do multiple choice depending on how it's set up. So I think that's probably the least important point I made in the talk, and
So
probably
good.
the most controversial. So I'm happy to, I'm fine with ceding the ground on that.
Any other questions?
Hi, thank you for your talk. I agree with most of your points, except for the multiple choice one. But we've actually already looked at the skill type one. We actually have a poster here on that exact topic
Okay, cool.
about and considering new metrics. So it'd be great to have you see what we did and see if we can talk more about it.
Yeah, so thanks. So I would really like if during lunch or something, maybe anyone who's interested, we could talk about a more concrete action plan.
Devi, your question?
What do you think of fill in the blank versus multiple choice to sort of just get rid of some of the complexity control that you can sort of arbitrarily inject into multiple choice by choosing options accordingly?
I think fill in the blank is kind of similar to multiple choice to me, because you could always, I think also like the way that I view multiple choice is basically as an entailment problem rather than a question answer, because it turns into like, you know, did the chicken cross the road? Yes. So you're entailing the chicken cross the road. So I don't have a strong opinion on like a preference for the fill in the blank versus question answer. I think I should also mention that there are a lot of other interesting VQA data sets out there. So Madlibs that does the fill in the blank and the V7 data set. I'm also a little worried about that because having like 10 VQA data sets also can make it hard to compare across papers or put a lot of pressure on people to spend a ton of time somewhat unnecessarily evaluating the same thing across multiple data sets. And so that's part of why I would rather than having many different customized data sets, I would rather have like be able to parse the VQA data set so you run an evaluation once and then you can evaluate in all these different ways.
Questions?
Thank you for the talk. I think this was awesome and very helpful. I think Aishwarya is going to show some analysis around rarity and sort of measuring how much these models are going beyond pattern recognition. And so it would be useful maybe to talk at lunch to see if that should just be something standard that's part of the challenge and evaluation as opposed to just analysis at the workshop. About the skills, we had thought of this earlier when we were releasing the data set if we should break it down by question types. Our fear was that then people might start writing a paper on just one particular question type and reporting accuracies on just that. So there was a fear that if it's a little too narrow, then it might just create more diversity where we have all these models that can either count or they can recognize colors, and then there's nothing that can sort of do things more generally. So that might also come down to the specifics of what this list of skills is. And so I guess the question is, how important do you think it is to be able to take a question and identify exactly the skills that are involved? Because things like whether a question needs external knowledge or not, it's hard to define what qualifies as external knowledge versus not. And should we be afraid of trying to identify a crisp definition, or do you think as long as it's qualitatively reasonable, that's much more useful to the community and we shouldn't worry about sort of the corner cases and so on?
Yeah, I think it's good enough is good enough. So I think it's not too important to try to be very precise about the definitions. It should be the case that those that are labeled with external knowledge, for example, people would generally agree that they tend to require external knowledge more than ones that aren't. In terms of like, will this encourage people to just focus on one single slice of VQA? It's possible. That wouldn't necessarily be a disaster, though, and one way that you can try to mitigate that is by also giving a best practice of, for example, always reporting overall, or if you're going to report a skill breakdown, report the entire table. So you could try to get people to, even if they're focusing on one thing, to not hide their performance on the rest of it.
Looks like we have one more. So I guess this will be the last question.
Thanks. So I guess if you break down by skills, I guess there was a feeling at some point that not all the questions are answerable by only the data. If you break down by skills, you can actually know what data to put in to actually get like the system to answer those questions, like set reasoning. If there's only like 1,000 examples, if we know there's set reasoning, we can collect the right data.
Okay, yeah, good point. Just to be clear, though, one thing I guess I wasn't. The skill attributes would be something that are used like I was thinking of it as something used post-evaluation rather than being an input to the system. I'm not sure if that was clear, but yeah, I agree with that point.
Let's thank Derek again. So now we are moving to the challenge part of this workshop. We'll provide a brief overview of the dataset, the challenge, and announce the winners. But before that, I would like to mention that this year, the challenge was hosted on EvalAI, which is a new evaluation platform, as opposed to last year, where it was hosted on CodaLab. So I would like to invite Deshraj, who is the team lead on EvalAI, to tell us more about EvalAI. Deshraj is a graduate student at Georgia Tech, and he is the lead developer on CloudCV, which is an open source cloud platform providing computer vision APIs. So Deshraj, we're looking forward to hearing from you.
It doesn't have VJ, Thanks, Ashwara, for the introduction. Hi, everyone. I'm Deshraj. We work at CloudCV. CloudCV is an open source organization which aims to simplify the process of AI research. Today, I'll be talking about our latest project called EvalAI. This is our team. We are a group of graduate students, engineers, researchers, and more than 30 open source contributors who have been actively contributing to our projects. The problem is benchmarking progress in AI is hard. Comparing new methods with existing methods is a crucial part of research, and in field as fast moving as AI, reproducibility is really important. But in the coming years, it has been found that comparing new methods with existing is hard due to following reasons. The first is differences in algorithm implementation, or use of different splits of the same data set, or not using consistent evaluation metrics. To benchmark progress, several AI challenges has been proposed. For example, in computer vision, we have the MS Coco challenge, ImageNet challenge. In data science, we have the KDD Cup, Netflix challenge, and so on. But there is still a lack of proper centralized platform to host and participate in challenges. So we introduced EvalAI. EvalAI is a web platform that aims to help students, data scientists, engineers, researchers to host, collaborate, and participate in AI challenges. Yeah, so this is the first thing that comes in everyone's mind. Okay, how is it different from Kaggle? Doesn't Kaggle already do this? So the answer is no. So EvalAI is a lot different than Kaggle. Kaggle doesn't support custom evaluation metrics. It has a list of evaluation metrics that you have to choose before creating a challenge on Kaggle. But EvalAI contains custom evaluation metrics, and you can create number of phases in a particular challenge. Also, EvalAI is open source, but Kaggle is not open source. To create a challenge on EvalAI, there are two main components. So the first is challenge host. The second is a challenge participant. So now I will be talking about what are the features given to challenge hosts and challenge participants in EvalAI. Since EvalAI is open source, the challenge hosts can fork EvalAI from GitHub, and they can deploy it on their own servers to run a challenge on their forked version of EvalAI. Yeah. Since I already told, EvalAI supports custom evaluation metrics and phases. So you can have your own evaluation script and use it to evaluate the submissions that the participants will do. Also, it also supports different number of phases for a particular challenge. So for example, in VQA challenge, we had 3 phases. So this is one of the screenshots that I've shared. Also, hosting a challenge on EvalAI is really simple. So so there are 2 ways to host a challenge on EvalAI. Either you could use the intuitive UI that we provide to host challenge on EvalAI, or you could use another method of uploading a zip configuration file. Yeah, so moving ahead for participants. So EvalAI provides a swift and robust backend that uses MapReduce at the backend, and it speeds up the evaluation on the fly. So just to give an example, as its first challenge, we hosted the VQA 2.0 challenge this year on EvalAI. To give some background, VQA 1.0 challenge was hosted on Coda Lab last year. The size of the dataset was 244K for the test set, and the average time of evaluation was 410 seconds. This year, VQA team released a VQA 2.0 dataset that was almost twice as the previous one, but this time the challenge was hosted on EvalAI, and we found out that our parallelized evaluation resulted in an overall 6 times speed up. So, and it took an average of 136 seconds for an average evaluation on test set. And overall, it was a 6 times speed up. Yeah, moving ahead, EvalAI provides a centralized leaderboard for all the challenges so that both participants and challenge hosts can track progress of each challenge. Yeah, also for the submissions, so whenever a participant does a submission, so they don't need to refresh the page to keep track of their submission status. The submission will be automatically updated on the UI. Yeah, talking about the progress of EvalAI project. So we have been supported by 30 plus open source contributors who have been actively participating and actively contributing to this project. And yeah, so just to give some context, we started this project in November 2016, and it has come along. And currently we have more than 1,100 pull requests and issues on GitHub. Also, we have been participating in Google Summer of Code for last 3 consecutive years, which has helped us a lot in developing our projects. So now I'll be talking about upcoming features on EvalAI. Recently, so creating a challenge on EvalAI can be done by 2 ways. So recently we released a challenge creation using zip configuration in the last week. You could go to evalai.cloudca.org and start creating a sample challenge if you want to do. So we are also working on this feature of creating challenge using intuitive UI, which will be released really soon by first week of August. Then the next feature on which we are working on is, suppose a challenge is hosted on any third-party website, and so if the challenge host want to feature his challenge on EvalAI, then they could just integrate their challenge with EvalAI using a simple webhook service on which we are working on, and that will help the challenge host to send results to EvalAI server without even taking the headache of so basically this will provide a centralized platform to showcase the numbers and results for the particular challenge. Yeah, so the next important feature is Eval Python APIs. So most of the researchers like to work on terminal. So we are working on building Python APIs so that they could send submissions to Eval server using just terminal and not opening the UI of Eval. To summarize, we are trying to build a centralized platform so that students, data scientists, researchers, they can come and they can host challenges, they can host, participate, and collaborate in AI challenges that are organized around the globe, and they can find everything about AI challenges on Eval. Yep. So if any of you is interested in hosting a challenge, we can talk offline after the workshop, or you can reach out to us at team@cloudcv.org. Thank you. That's all from my side.
Thanks, Deshraj. In the interest of time, maybe we can take few quick questions.
So you already compared to CodaLab. So CodaLab allows you to host it on their servers, but in this case you need your own server.
Since Evalia is open source, so either you could give your annotation, you could give your evaluation script to us, and we will host challenge on our own servers. Or otherwise, this is also open source, so you could ideally deploy it on your own private servers and host the challenge of your own there.
So will there be a risk if we let you host it, will there be a risk at some point if it gets really popular that it will have the same issues as CodaLab has? Because right now it sometimes runs into all kinds of problems because there are so many challenges running there.
Yeah, agree. So basically, before building this platform, we have researched a lot. So we have researched about the CodaLab evaluation, like how do they evaluate, since their code is also open source. So we found out that they use sub process that creates a lot of problems. So for every submission, what they do is they load the test annotations or other files that are required to evaluate. But in our case, like we have the workers set up in such a way that it loads the annotations and the questions files and all other required files that are needed to load. It loads once and it just runs the submission on the fly. Yep.
Thanks, Deshraj.
Yep.
Now, Yash is going to provide an overview of the dataset and challenge.
Right. Thank you everyone for coming. My name is Yash, and Aishwarya and I will be giving a quick overview of the dataset and the challenge before announcing the challenge results, which you all have been eagerly waiting for. For those who are not familiar with VQA, I will first recap the task definition. Then I will talk about VQA version 2 of the dataset and this year's challenge. And then Aishwarya will announce the results. And finally, we will go over some interesting analysis of the results. So let's start with the task definition. Given an image and a natural language open-ended question such as what is a mustache made of, the task for an AI system is to generate a natural language answer, bananas. To facilitate progress in this research area, a large-scale dataset, which we will call VQA version 1, dataset was released in 2015. These are some examples of questions from the dataset. Some questions are about objects, what is a mustache made of? Some questions are about fine-grained recognition, is this vegetarian pizza? Some are counting questions, how many slices of pizza are there? Some questions are about common sense. Does this person have 20/20 vision? The VQA version 1 of the dataset contained more than 250K images, more than 750K questions. Each question has 10 counted answers. Overall, there are about 10 million answers. The accuracy metric counts how many of the 10 counted answers does the machine-generated answer match with. If it matches 3 or more, the prediction gets full credit. Otherwise, it gets partial credit corresponding to the number of counted answers it matches with. But the VK 1.0 dataset contained strong language priors. For example, 41% of the questions starting with what sport is can be correctly answered with tennis. 39% of counting questions can be correctly answered with 2. And so is the case with other types of question engrams. These language priors can give a false impression that machines are making progress towards the goal of understanding images correctly when they're only exploiting these statistical biases. To solve this problem, we propose to reduce these language bias by balancing the dataset. In fact, we balance each question in the dataset. So for each question answer image instance in VK 1.0, we find another image I dash, which is similar to image I, for which the question makes sense, and the answer A dash is different from the original answer A. Now for the same question, there are 2 images with different answers. So the model really needs to look at the image to predict both answers correctly. Any blind model exploiting language priors will, by construction, get one of the 2 wrong. VK 2.0 is particularly difficult because the new image is semantically closer to the original image in FC7 feature space. Therefore, VK models will really need to understand the subtle differences in the images in order to correctly answer the question in both cases. For example, for the question, who is wearing glasses, VK 1.0 dataset contains an image where the answer is man. Our VK 2.0 contains another image for which the answer to the same question is woman. It is important to note here how semantically similar these 2 images are. Both have 2 people next to each other, and exactly one of them is wearing glasses. In both pictures, our VK system needs to recognize where the glasses are and the gender of the face closest to the glasses to answer this question correctly for both images. Now let's see how we balance each question using an example. Given this image and the question, what game is this, with the answer tennis, we go to Mechanical Turk and show humans 24 nearest neighbors of the original image and ask them to select an image for which the answer to the question, what game is this, is not tennis. So for example, the worker can pick this image. We then further collect answers for this image. Now let's look at some examples of these complementary pairs. For the question, is the umbrella upside down? The answer is yes for the left-hand side image, and the answer is no for the other image. For the question, what color is the hydrant? The answer is red for the first image and black and yellow for the second image, and so on. More concretely, we observe that the answer distribution is more balanced now. For all questions starting with is there, we can see that the VK 1.0 dataset has a rather uneven distribution, with 79% of the answers being yes. In VK 2.0, we find the new distribution to be almost equal for the 2 answers, yes and no. These trends, where the distribution is more spread out now, can be seen for other question types in the dataset. Quantitatively, we find that the entropy of answers averaged across question types increases by 56% from VK 1.0 to VK 2.0. So the VK 2.0 dataset contains more than 200K images from Coco, more than 1.1 million questions, and 11 million answers. Hence, VK 2.0 is about 1.8 times larger than VK 1.0. Now that we have reduced these language priors, we benchmark some representative VQ models from last year on VQ 2.0 and compare with VQ 1.0. We found that when these models are trained on VQ 1.0 dataset and tested on VQ 2.0 dataset, the performance drops by 6 to 7%. When these models are retrained on VQ 2.0 dataset, they gain 1 to 2% accuracy back. Note that we use half of the VQ 2.0 train set, which is of a similar size as VQ 1.0 train set to be comparable. Further, when we train these models on complete V2 trained plus val set, the accuracy further improves because of more training data. If we look at specific subsets of questions, we observe that the biggest drop is for yes/no type questions. This is great because most of the top entries in VQ Challenge 2016 achieved very high and similar accuracy on yes/no type questions because of the language biases present in VQ 1.0 dataset, which we have substantially reduced in VQ 2.0 dataset. So now there is more scope to develop more intelligent models that need to really look at the image to get the answer right. We will see more of it in the analysis of challenge results. So that was about the task and dataset. Now let us look at the VQ challenge. The VQ challenge is hosted on Eval AI, which Deshraj talked about earlier. The training set consists of 80K images and 443K questions. The validation set is about half the size, consisting of 214K questions. And the test set is about the same size as train set, consisting of 80K images and 447K questions. Let's look at the test set in more detail. Following last year, the test set is divided into 4 splits of approximately equal size. The test self split is for the purpose of debugging and validation. The test standard is for public leaderboard. It has a limit of 5 submissions and max 1 submission per day. This set is also meant for reporting numbers in the paper and comparing with other methods. Test challenge is a split used to decide the ranking of the challenge participants. And test reserve, which includes some additional questions we added this year, is for making sure that there is no overfitting. Scores on the split are never released. Now Aishwarya will announce the winners.
So now it's the time to announce the winners. I'm sure you all are waiting for that. But before we actually announce it, I would like to mention that this year we had 24 teams participating in the challenge with individuals from about 26 institutions across 8 different countries. And these stats are based on the responses that we have received. So now I'm going to announce the winners and the runner-ups. And I would like to request the teams to come onto the stage and get their awards as I announce their names. So this accuracy is 68.16. Let's have a big round of applause. So the award is NVIDIA GPU. The other team, the other team at second position is DLAIT, and the team members are Yongchul Son, Kibam Lee, John Riol Lee, Gyute Park. They are from Samsung Electronics, and the test challenge accuracy is 68.07. So now it's the time to announce the winners. I would again like to request the winner team to come onto the stage and receive the award as I speak out their names. So the award for the winner team goes to Adelaide Tenney ACRV MSR team, and the team members are Damon Tenney, Peter Anderson, David Golub, Posen Huang, Lee Zhang, Xiaodong He, and Anton von der Hengel. And the challenge accuracy is 69%. So now let's look at some analysis of results. So this plot shows the challenge accuracies for top 20 teams which participated in the challenge. The green bar is the MCB model. It is the single best model of the challenge winning entry from last year, benchmarked by us on VQAV 2.0. As we can see, there is significant improvement in the performance compared to the MCB single model, with an absolute improvement of about 7%. It is worth noting that of teams are statistically significantly different from one another. We bootstrapped samples from predictions 5,000 times and report statistical significance at 95% confidence. So this plot shows groups of teams which are statistically significantly different in different colors. We can see that the challenge winner is statistically significantly different from everyone else. The team at the second rank is statistically similar to the team at third rank, but is better than rest of the teams. Hence, we decided to award second and third teams joint second position. We were curious to know if there are certain questions which none of the top 10 teams could answer, and if there are certain questions which all of the top 10 teams were able to answer. So we made this plot where the x-axis shows the number of teams out of top 10 that were able to correctly answer certain questions, and the y-axis shows what percentage of questions they were able to answer. So the first bin shows the percentage of questions which none of the top 10 teams was able to answer correctly. So these are difficult questions, which also means that 85% of the questions could be answered by at least one method. The last bin shows the percentage of questions which all of the top 10 teams were able to get it right, and hence we call these questions easy questions. The shaded plots are the same, the plots reporting the same stats from the last year, just for reference. It is to be noted that the set of difficult questions also include those questions whose ground truth answers are not in top K answers. So methods which use classification over top 1,000 answers will not be able to get these questions right. So we found that about 50% of these difficult questions are those whose answers are not in top 1,000, and we would like to see how these questions look like qualitatively. So this visualization shows such questions whose answers are not in top 1,000. The innermost arc contains the first word of the question, and the next arc contains the second word, and so on. So some of the examples of these questions are: what is the name of, what is the number on, what is written on the, what does the sign say, what kind of, what type of, what time is it, why. So it is interesting to note that most of these questions are OCR types question, some are fine-grained recognition question, and others are open-ended such as why. We compared the trends from this year to last year, and we found that this plot looks more or less the same, which shows that we still need to improve our models on these type of questions. Now we would like to see how the easy questions are qualitatively different from those difficult questions whose answers are in top 1,000. So the left plot shows the difficult questions whose answers are in top 1,000, and the right plot shows the easy questions. And we can see that easy questions have higher percentage of binary questions, which are answered with yes, no, whereas the difficult questions have higher percentage of how many questions. So the VQA models are not good at counting. It is interesting to note that for the questions which are answered with number, the team which is at 4th rank overall is actually outperforming the winner team for those questions. And for other types, which is yes, no, and other, no team is statistically significantly better than the winner team. Okay, so as Yash explained, the VQA 2.0 dataset has 2 images with the same question but different answers. And these images are very similar to each other. And we call these images complementary images. So given such a dataset, it is interesting to analyze if the models are sensitive to subtle changes in these complementary images. So in order to answer the question, are models sensitive to subtle changes in the images, we analyze if the predictions are different for complementary images given the same question, and we also analyze the accuracy of the model if the metric is how many pairs you got right. So in this plot, we show the percentage of questions for which the predictions are different for the complementary images, and we see that most teams predict different answers for about 60% of the pairs, and there isn't much difference across teams. We can also compute the same statistic for the MCP model, which was trained on V1 data. And we can see that for this model, it has lower percentage of questions for which the answers are different. Hence, training on V2 leads to higher percentage of questions with different answers, with 16.5 absolute increase. Now we report the accuracy of each model when the accuracy metric is how many pairs you got right. So under this metric, if a model predicts correct answer for both images, it gets 1 point, otherwise it gets 0. So we can see that the top teams get about 50% of the pairs correct. We can also see that certain teams change their relative ranking compared to their ranking on the overall accuracy metric. So for example, the VQA machine team outperforms the 2 teams in front of it when the accuracy metric is the pairwise accuracy metric. And again, we can look at the accuracy of MCB model trained on V1, and we can see that it is quite below the accuracy of the models trained on V2. So basically, training on V2 data leads to about 11% increase in the pairwise accuracy metric. It has been shown by recent studies that today's VQA models are driven by superficial correlations in training data. So it is interesting to ask how many of the current entries are driven by priors in the training data. So in order to answer this question, we compute the accuracy over those questions whose answers are not popular answers for the given question type, which is basically the first few words of the question. We further divide this analysis into 2 categories. The first is we consider all those questions whose answers are not the top 1 answer for that question type. And then we consider all those questions whose answers are not in top 1 and also not in top 2. So in this plot, we show the accuracies of all the entries for those subset of questions whose ground truth answers are not in top 1. And so those accuracies are blue bars, and we call that non-1 prior questions. And we compare those accuracies with the accuracy on the entire data set, which are the red bars. And we see that there is a significant drop in the performance for every team. We can also compare how the relative ranks of the team changes using on this new subset of questions. And we can see that team June Flower outperforms the 2 teams ahead of this. Here we show the accuracy on those subset of questions whose answers are not in top 2. And we again compare it with the accuracy on all questions. And we see that in this case, the drop is even higher because the ground truth answer is not in top 1 and also not in top 2. So this shows that existing models are driven by priors to some extent. We can again look into the change in relative ranking. We can see that certain teams like LVNUS outperform the teams which were ahead of them on the entire data set. And hence this shows that some models are driven by priors more than others. Another interesting question to ask is how good are current models in answering questions which are compositionally novel. So what we mean by this is the following. A question is compositionally novel if the QA pair is not seen in training, but the concepts constituting those pairs have been seen in training. Let me explain with the help of an example. So in this case, the question, what color is the plate, with an answer red, is compositionally novel because the same question, what color is the plate, comma red, has not been seen in training, whereas the concepts such as plate and red, which are essential to answering this question, have been seen in training. So for such a setting, a model needs to be able to compose concepts to recognize novel composition at test time. So we figured out, we sorted out such questions from the test set which are compositionally novel, and we report accuracies of the current challenge entries on those subset of questions. And we see that the performance drop is significant compared to the performance on entire dataset. And we again see that there is some change in the relative ranking using on this new subset of questions which are compositionally novel. So teams like LV-NUS, they are now outperforming the two teams in front of them on the overall dataset. So this means that certain teams are better at dealing with compositionality than others. And here are some qualitative examples of the data points that teams got right and certain data points that they got wrong. So for example, here I'm showing the question and the two complementary images for the same question, and both of these were answered correctly. So the question is, how is the weather? And in one case, the answer is rainy, in the other case, the answer is sunny, and the model gets both of them right. Similarly, the question is there anyone in this room? And in one case, the answer is no, and in the other case, the answer is yes, and both of them are correctly answered. Again, the question is the sky bright? And in one case, the answer is yes, in one case, it is no, and both of them are being answered correctly. And similarly, in this case, the question is, what kind of animal is shown? On the left image, the answer is cow, and the right image, the answer is elephant, and the model gets both of them right. It is more interesting to look at the failure cases. So these are the failure cases where the answers predicted by the model are different for the two complementary images, but one of them is right and one of them is wrong. So the question is, what are the bears doing? In one case, the answer is swimming, which the model gets right, but in the other case, the answer is watching, but the model predicts playing, and hence gets it incorrect. In this case, the model predicts different answers, but gets both of the answers wrong. So the question is, what number is on the tent? In one case, the model says 1, and in the other case, it says 33, and both of them are incorrect predictions. In this case, the model is actually producing the same answer for the complementary images, and it gets one of them right and one of them wrong. And here again, the model is predicting the same answer, but it gets both of them wrong. The question is, how is the man looking? And the ground truth answer in one case is happy, and it is serious in the other case, and the model just says up. So now, another interesting observation is how is VQ 2.0, if we train the models on VQ 2.0 and test on VQ 2.0, are there some qualitatively different trends compared to VQ 1.0? So here's one trend that I'm going to point out. So for the top 4 entries from the last year of VQA challenge, if we look at the gap in the accuracies, so the gap in the overall accuracy was 3.5%. And if we look at further fine-grained gap, for yes, no, it was only 0.15%. For number, it was 1.51%. And for other, so the gap was highest for other questions. Now let's look what happens this time for top 4 entries. So this time, the overall, the difference between the overall accuracy is 1.38. But for yes, no, it is significantly higher than last time. And for number, it is 3.19. And interestingly, for other questions, it is the least. So this shows that for last year's challenge, a lot of improvement was made on other questions. And this year, it has kind of saturated. But this VQA 2.0 provides us new signals to benchmark models on certain, on on subsets of questions like yes, no, because we see more difference between the top 4 entries for yes, no questions on this data set. But we should note that although the gap between the top 4 entries is 1.38%, the gap between top 20 entries is significant. It is 7%. So that's all I had, and I would be happy to take questions.
Last time you had like split up how many models use like ensembles and so on. Do you have some similar idea how to split that?
Yeah, we did a survey last time to gather that information, and it was so like it wasn't very interesting in the sense that we knew like some teams are going to use and some teams are not, so we thought we might just drop it this time. Yeah, and we have method descriptions, which we are going to put up on the visual QA below the leaderboard. So if you are more interested, you can see the descriptions there.
In general, it might be interesting to get like single model performance and then present just VQA. So just train on VQA as a single model. That might be interesting.
We can still run it, and we can gather the stats, and we can maybe post it on our website.
Hi, I don't think you have done this yet because you may not have access to the models as such, but it will be interesting to see if you were looking in the pairs of questions which are answered correctly. So it will be interesting to see if the attention maps are actually focusing on the different parts of the images, and in the pairs which are wrong, did it fail because it didn't focus on those parts, or did it focus and still got it wrong? So that
Yeah,
might be
I agree. That would be interesting to look at. Yeah. And also it is only qualitative because we don't evaluate attention maps. So it will be few examples and we'll only be able to look at it qualitatively. So no more questions? Okay, so now I would like to invite the first runner-up team to present their talk. And so the team name is HDU USYT UNCC, and the team members are Zuyu, Dwinyu, Chen Chao Shan, Dalu Go, Jianpeng Fang, and Dan Chen Tao. And the team members unfortunately could not make it to the workshop, so one of their colleagues is going to present the talk.